Yeah, are you ready? Yeah, sure. So in the last class, we have seen up to Einstein coefficients, in which we said that basically stimulation emission is the one which we are getting the laser action. So therefore, out of all the three, things, that is absorption, spontaneous emission, and stimulated emission, we require to have stimulated emission. Therefore, you get the amplification. So with the amplification of the photon number, you get the laser light. So that's what we are interested. So therefore, we have derived. So with the Einstein coefficients relation, so we have derived the relation between absorption coefficient and stimulation coefficient. So no matter whatever happens, absorption coefficient and stimulation coefficient, stimulated emission, both will be same. But when it comes to spontaneous emission and stimulated emission, it depends on the frequency. Now, when you operate in the higher frequency range, then you get the spontaneous emission will be dominated. So therefore, you need to go to the lower side of the frequency in order to see the stimulated emission to be dominated. So before going to that stimulation emission, there is one video I wanted to share with you. I will show you here. Just see that. So there is a one atom. Now imagine, once it receives the energy, it goes to the higher energy level. There photon is coming. 2 photons are coming out. Yes, this is with respect to one atom. Now imagine the same thing happens with the multiple atoms. See, these photons are have you understood this? I'll just explain you what exactly it means. Did you get this sound, something?
No, sir.
Did you get the sound in this video?
No, sir.
No, you did not get the sound. All right, okay, okay. So there is, this single atom, you have it. Initially, it is in the rest position, which means rest position in the sense it is in the lower energy level, that's in the valence band. Then it has moved, after receiving some energy, it goes to the higher energy level. Now, when it is in the higher energy level, it has a lot of energy. So therefore, when it is in the higher energy level, imagine that if the photon of equivalent frequency with whatever it is absorbed, okay, so if it goes then interact with the electrons in the higher energy level, then it will release 2 photons. See, that's what it is happening. Okay, so if you make the same thing to the multiple atoms, it's not one atom. As I said, like there will be 10 to the power of 23 Avogadro number of atoms will be there. So each of atom, if it is having the same 2, then these 2 walls, this is called as a resonator, we call it as. I'll explain you about why this resonator, the 2 walls are very important, because it is in the, when you wanted to produce the laser light, there is a, essential components you need to have it. One of them is basically resonator, which means basically these 2 walls are partially reflected mirrors basically. So one will be completely reflected, another one will be partially reflected. So what happens is when photons are moving to this end, so to this end here, this end here, so then what happens, it gets completely reflected. Okay, when it gets reflected and it's going to interact with one more atom and it releases another set of photons now. So likewise, the multiplication will happen within the resonator with the multiple reflections. So you get the high amplitude of the photon numbers is getting multiplied here. So that's how you get, there will be in the resonator itself one of the partially reflected mirror. Through that you get the laser light out of this. So to make it clear, I will, I will make it this video once again to understand for your clarity purpose. See that once again. Okay. Have you understood this concept of stimulated emission now? Have you understood this?
So please once again, sir.
Once again, I need to repeat the video, or should I explain you?
Sir, explain, sir, explain.
All right. Okay.
Yes, sir, please.
Yes. Sure. Definitely. See this stimulated emission process. Now imagine what is happening is when the atom is at the higher energy level here. Okay. When photon interacts here with the when your atom is in the or electron is in the higher energy level. Okay. When some of the photons comes and interact when it is in the higher energy level, then what happens? Two photons will be emitted. That means now this atom having two photons, because one it is here after receiving some energy here, it is moved to higher energy level. So now the same amount of energy of the photon again you are giving, identical photon you are giving. So now which means this atom consists of how many atoms now? Photons now? Two, right? Isn't it? One is received at the higher energy level, the other one received here at the lower energy level. Correct?
Yes, sir.
Yeah. Now since the atom, when it is in the E2 level having two photons here, so it has excess energy. So with this excess energy, what all it can happen is it can go either in the upward direction if any available states are there. Imagine that there are no available states. Okay. Now what it is supposed to do? It has to forcefully come down. Correct? So when it comes down, it will release that two photons, whatever it has received. Now these two photons are identical, so therefore it will have the same wavelength, the same coherence, and same intensity. So therefore these two will release in the same direction. Now imagine that these two photons, whatever it is released, right? As I said, like there are two, resonator walls. It gets reflected and it comes down. Meanwhile, if there are any other atoms in the higher energy level, now again these two photons will interact with two more atoms. Okay, these two photons, if it interact with the two more atoms in the higher energy level, how many number of photons will be released at this time? If these two photons interact with the two more atoms in the higher energy level, how many number of photons it's going to release now?
4, sir.
4, exactly, right? Each one have 2 now. So therefore total 4 number of photons will be released. Now these 4 photons also again go and interact with 4 more atoms. Now as a consequence, how many number of photons will be released?
16, sir.
8. 8. Right?
8,
So these
yes,
will go again and interact with the 8 more atoms, it releases 16. Like that, this is a geometrical kind of progression takes place. So the multiplication of the photons is going to take place in that way. So for that video I have shown you. Okay. So now in this spontaneous emission, what happens? There is only one photon it has taken and it has gone to higher energy level, and while it comes back, it is released one photon. That's all. There is nothing now. But whereas in the simulated emission, when you expose, external light here at the when it is in the higher energy level, then you get the stimulated emission process. There you get the identical photons, released in the same direction, because all these photons are identical. So therefore, it will have the same energy, same wavelength, and same phase difference. All that you will have same. So therefore, that will be released in the same direction. So that's how you will have a stimulated emission process. Okay. So now imagine if you have only two energy levels, if you have it. Okay. So now under ordinary conditions, most electrons are in the lowest possible energy level. But process called population inversion, we can create an environment in which more electrons are found in the excited state. This is a statement in a way, basically. So this is what is known as population inversion. Population inversion is nothing but having more number of atoms in the higher energy level than the lower energy level. That is called population inversion. So as I said in the last class also, like most of us, imagine that I and you, every one of us is like atom. right? So atom wanted to be in the stable state always. So when you get the stability, when you are in the lower energy level, right? So therefore, in general, atoms will try to be in the lower energy level in order to have the stability. Okay, but this stable process will not give you the laser action. So therefore, what you need to do is you need to create the population inversion. Population inversion in general, basically, you will have large number of atoms in the lower energy level. Only few will be in the higher energy level, right? So, but inversion of this one is called population inversion. So, population inversion is nothing but so creating more number of atoms in the higher energy level compared to lower energy level is called population inversion. So how do you create it? Now, to obtain this process, you need to have metastable state. Now, why do you need metastable state? That you need to understand. Imagine that when you have only two energy levels, let's say you have only two energy levels you have. Imagine that you will have four atoms initially at the ground state. Now, by some process like, by giving some external radiation, at the most you can actually send only out of four, two atoms in the higher energy level and two will remain in the lower energy level. At the most, you can only pump 50% of the atoms to the higher energy level. The reason is basically because by the time you send the third atom to the higher energy level, the first and second will come down. Because again, the lifetime of the atoms in the higher energy levels will be in the order of microseconds or milliseconds. It's in the microseconds, like 10 to the power of minus 8 seconds, 100 or 10 nanoseconds in a way. Okay, so it will be in the 10 to the power of minus 8 seconds. Within 10 to the power of minus 8 seconds, it's come down to the lower energy level again. So therefore, if you have only two energy levels are there, then what happens is you will not be able to pump or you will not be able to create a higher energy level with the more population. So it's impossible. So therefore, you need to have some other energy level to create the population inversion. And that energy level or state is called as metastable state. Now, how do you get this metastable state? How do you get this metastable state? Any idea? What is this metastable state again? So name itself is telling it's not, metastable means stable means very relaxed, isn't it, right? Metastable means either it is, stable or no, it's not, neither stable nor unstable. It's somewhere in between. Meta state you call it as. Okay, it is somewhere in between. Basically, this one you define with respect to how much time atoms can stay at that particular level. Now imagine that, as I said, this one in the lower energy level you will have longer time, right? And at the higher energy level, I said like 10 to the power of minus 8 seconds. And somewhere you create in between one more state, and at this state, if atom stays for some 10 to the power of minus 3 seconds, that should be long, in a way it's like more, right? Isn't it, right? In a way, it is like lifetime is higher compared to 10 to the power of minus 8, 10 to the power of minus 3, which means 1 lakh folds it is higher. So 1 lakh times it is the atom is staying longer time compared to higher energy level, isn't it, right? 10 to the power of minus 3 seconds means very, very high in a way. Okay, so that's what is metastable state. So you need to create a metastable state in order to achieve the population inversion. Now, again, I'm repeating here, population inversion is about having a system with a large population of electrons in excited state than the ground states. This also requires excited state to have a relatively long lifetime so that protons can continue to encounter excited electrons. So when you have atoms or electrons in the higher energy level, therefore you can actually, externally at that time, when these electrons are at the higher energy level, for longer time, then you can expose these electrons to the external radiation again, so that you get this stimulated emission process. So once population inversion is achieved, the rate of stimulation emission will dominate over rate of absorption. So that's how you get the amplification process. Okay. Now, So in order to get the light amplification to work out, it is necessary to have enough excited atoms for the photons to continue the process of stimulated emission. So the point is that you need to have more number of atoms in the higher energy level. Now, population inversion again, population inversion is a state in which more atoms are in excited state compared to the ground state. To achieve this population inversion, optical pumping is required. So, which means, what is this optical pumping? Optical pumping means sending the electron from the lower energy level to higher energy level. Pumping is nothing but sending your electron from the lower energy level to higher energy level. Now, how do you send it? Optical pumping. Optical means you are using light. Right? Basically, you use light now. Right? So when you use light with for sending your electron from one lower energy level to higher energy level, then it is called as optical pumping. Or some other pumping mechanisms also there. I'll come to that little later. But just at this moment, you need a pumping process to get the population inversion. Okay. Now another metastable state again. Normally, the mean lifetime of the excited atoms before spontaneous emission occurs is 10 to the power minus 8 seconds. However, for some atoms, some excited atoms, this mean lifetime is perhaps as much as 10 to the power of 5 times longer. So these states are called metastable states, which means basically, as I said, like you need to create one more, energy level where at that energy level the lifetime of the atoms will be 10 to the power of minus 3 seconds harder. So if you have that, then atoms will be staying at that level for longer time. So that means basically you can expose the atoms in that level for longer time with the external radiation. So that you can be total population inversion, then you get the stimulation emission process to trigger. Is this clear? What is metastable state and what is population inversion? This is very, very important. Unless you understand this, I'll not be able to go further. If you have any doubt, yes, please.
Sir, once can you discuss metastable states, sir?
Once again, I will discuss metastable. Okay, all right. So I'll take one more empty slide. Yeah, here I'll take it. Yeah. See, if you have only 2 atoms are there. Let's imagine that there are only 4 atoms. Okay. Now, as I said, like there is something called pumping. What is pumping? Pumping means basically, you give external energy. Pumping is nothing but giving the external energy. External energy when you give to lower energy atoms, then these atoms will excite to the higher energy level. Okay. So when you give pumping or when you use pumping mechanism, these out of 4 atoms, at max, theoretically you can talk about, at max you can get only 2 atoms you can send it to the higher energy level. By the time you try to send the third, what happens is these 1 and 2, because this higher energy level lifetime will be only 10 to the power of minus 8 seconds. In a fraction of seconds, as soon as you send it, then these 2 will come down. Okay. By the time you try to send the third one, first and second will come down. So at any point of time, you will not be able to see 3 atoms in the higher energy level, but only you can see at most 2 in the higher energy level and 2 in the lower energy level. Is this okay?
Yes, sir, up to here clear.
Up to here it is clear, right? Now, at this moment, now how do you create the population inversion? Because we have seen in the Einstein coefficient, right, probability of 2-1 is actually proportional to N2, number of atoms in the higher energy level. Am I correct? For the stimulated emission process, right? So that means unless you have more number of atoms in the higher energy level, you'll not be able to get the stimulation emission process. So having this more number of atoms in the higher energy level is called as population inversion. Having more number of atoms in the higher energy level is called population inversion. Okay. Unless you get the population inversion, it is impossible for you to get the stimulated emission process to trigger. All right. So therefore, you wanted to have some another. Now, here itself, I can tell you one more statement. So therefore, you can say that if you have only 2 energy levels, only 2 energy levels, it is impossible to get laser light. Okay, so in two level system, when you have only 2 energy levels, it is highly impossible for you to get the laser light. So therefore, you have to have 3 levels. That is 3 energy levels I am talking about. Okay, so 2 energy levels are not sufficient to get the laser light. Please remember, this is a very, very important statement basically. Okay, 2 energy levels are not sufficient to get the laser light to produce. So therefore, you need to have at least 3 levels. So that third level is something called as metastable state. It is something called as metastable state. And what is the advantage with this metastable state? You create it, metastable state. How do you create it? I'll explain you in a minute. Okay. But this metastable state, the lifetime will be something like 10 to the power of minus 3 seconds. Imagine that this is where somewhere you introduce the metastable state. 10 to the power of minus 3 seconds. Okay. Now what happens is when you excite these 2 atoms here, okay, when you excite these 2 atoms, within no time these 2, will try to come down. Now when it try to come down, it see there is another energy level is there. Therefore, these 2 atoms will come down here. Okay. Now third atom you try to send it here. Now how it is distributed now? 1 is in the higher, 2 is in the metastable state, and 1 more in the ground state. Now imagine second 1, 2, and 3. No, between 3 and 1, there is a population inversion is achieved for some fraction of second, isn't it right? For a time of some time, like for time delta t, there is a population inversion achieved between third and 1, isn't it right? Right? Maybe this may not be continuous. Okay, this may not be continuous. Just being line. నా క్లాస్లో ఉన్నాను ఒక్క నిమిషం నేను చేస్తాను నేను వచ్చింది అరుణా సార్ చెప్పాను యాక్చువల్గా సార్కి పంపించాను కూడా కన్వర్షన్ అది కంపారేటివ్ వన్ తెలుసు నాకు అది వచ్చిన తర్వాతనే అందుకే నేను ఈ కంపారేటివ్ చార్ట్ అరుణా సార్ పంపించి ఒకసారి చెక్ చేసి ప్రాసెస్ చేయమని చెప్పాను ఎందుకంటే సారే ఇనిషియేటర్స్ అయినది ఓకే ఓకే నేను మళ్ళీ కాల్ చేస్తాను I'm sorry.
Sir?
Yeah. Yes, please. Yes.
Sir, but actually you define the population inversion as there must be minimum of 3 electrons, like 3 electrons on the same level.
No, I did not say. Population inversion, I said, having more number of atoms in the higher energy level compared to lower. That is what I said.
Oh yeah, okay, sir. Then in the sense we are getting only 2 electrons now, even though we are taking the metals.
That's okay. No. I just gave you only 2 and 4, man. Okay. For your understanding purpose. Okay. I choose only 4 here, but in reality, only 4 will be there. 10 to the power of 23. For your understanding purpose, I am giving you 4 and 2, 1.
Yes, sir. No.
All right. This is only for just clarity. That's all. Okay.
Yes, sir. I got confusion that only 2 are there.
Yes. No, I understand. But basically, this is not with respect to 1 or 2, right? Obviously, you'll have, if you take 1 centimeter square, right? Or in a way, volume, if you take it 1 centimeter cube, you'll have Avogadro number of atoms will be there. 10 to the power of 23 will be there, right? And definitely, you'll not be able to count it, obviously. Please remember that. Okay, so you need very fine instruments to see how many number of electrons are there. Yes, you can do that. How many number of atoms are there in the electrons are there in these energy levels, that you can actually calculate with some of the experimental methods, but you need to have a precision measurements required. Okay, so but what I'm trying to give you a gist of it, I'm trying to explain you with a very small analogies or examples. That's all right?
Yes, sir. Got it, sir.
Yes. Now now since the the metastable state having lifetime higher compared to the higher energy level, so therefore atom will stay for longer enough time to be in the metastable state. So in that meantime, you will see a population inversion between 3 and 1 is achieved. So when you achieve the population inversion, obviously you get this stimulated emission process to trigger, because when these atoms are at this metastable state, when since it is in the population inversion, so therefore you try to expose, external radiation here, then you get the, the number of photons will be released again, and those photons will be in the, identical, and you get the laser light. Okay, so that is one process. Now the question again you need to answer: how do you get this third state, metastable state? How do you get it? That is very important. Okay. Now imagine, I'll just give you a simple example. Let's say, many of the lasers, when you are talking about, so best examples are basically CO2 laser, helium neon laser, and argon laser. Then NdArg laser, you have it. Okay, NdArg laser. So all these are material-based lasers, basically CO2 laser, which means carbon dioxide laser, and you have a helium neon laser, which means basically what it says is CO2, meaning what, one carbon is attached to two oxygens, isn't it right? One carbon is attached to oxygen. Now, when you are working when you look at actually all these atoms, let's say, again, I'm giving you a rough number. Imagine that you have a 200 carbon atoms. You have a 200 carbon atoms. Okay. Now, for 200 carbon atoms, how many number of oxygen should be there?
400.
400 should be there. Okay. But in reality, when you actually take some materials, you will not exactly get to, for 200 carbon atoms, 400 oxygens will be. No, it won't actually happen. So there will be always some sort of defects will be there. So let's say, for 200 carbons, you'll have only 390 oxygens will be there. 390 oxygens will be there. There will be some deficiency you will have it. Maybe 395 oxygen will be. So 5 oxygen atoms will be missing. So that missing is nothing but, missing of electron is nothing but hole, isn't it right? Isn't it right? Missing of electron is nothing but hole. Am I correct?
Yes, sir. The hole is clear.
That we call it as, a acceptor. So, for example, you remember your, +2 semiconductor physics. There is the acceptors and donors, right? Donor is nothing but the one which ready to give the electron. Acceptor is nothing but the one which ready to take the electron, right? Donor is having the negative charge, and the acceptor will be having the positive charge. And these acceptors and donors also will have some energy levels, isn't it right? Likewise, when you have the defect in the carbon dioxide itself, there will be one energy level will be there. And that energy level you will have. That energy level is nothing but like a, a defect state. It is called as. It is called as a defect state. Defect state. Okay, or defect energy level. All right, and this energy level will be somewhere between the higher and lower. And this is called as an impurity state also. Let's say defect energy level can be anywhere between the, higher energy level and lower energy level, because the energy of this one will be, valency band to higher energy level in between somewhere. So therefore, you can consider this as a metastable state. Okay? And another example, like, apart from defect, you must have heard about the doping. Have you heard of doping?
Yes, sir. We heard it.
What is doping?
So
what is
like
doping?
making the semiconductors more effective.
Absolutely, exactly. So making your semiconductor material, pure semiconductors, into impure one, right? Impure one. So, for example, you must have remember gallium phosphate is something called as impurity semiconductor, right? This is called as p-type semiconductor, in other words, right? So, like adding some trivalent impurity atoms to the gallium atom, or you take, let's say, silicon, and you add arsenic atoms to that, then you will get the n-type semiconductor, right? Depending upon the impurity atom, some impurity atoms you are adding it to the pure semiconductor. Now this impurity atom is nothing but, it is impurity is nothing but atom only, right? Isn't it right? You are trying to replace the original atom with some impurity one. Okay, isn't it? So now, which means the original atom will have valency and higher energy level, and the doped one, right? The impurity atom also will have some energy level, isn't it right?
Yes, sir.
Now that energy level, it will be somewhere in between these two higher energy levels. All right. And now, are you getting how you create the metastable state? This metastable state can come by impurity atoms, by defects, or some other means. All right? Are you getting? Yeah.
Sir, one small doubt, sir.
Yes, yes.
Sir, the electron inside the atom will be excited, right?
Correct.
But as of now, I think this excitation will not be relative. No, means like individual atom, it depends upon the energy it absorbs. The electron will be exciting. The other atom cannot influence the first one now.
No. What happens is, see, this need to be a longer vision. You should, visualization. You should have it. Now, when I'm talking about with respect to one atom, it's not one exactly I'm talking about. Imagine that where here somewhere I spoke about maybe if you recall the video itself, there is one atom I spoke about. Then you see there are multiple atoms are coming in between. Correct? So, for our understanding purpose, I am trying to tell you about with respect to one atom. But whatever is the process, when you shine the light to material, are you giving it to only one atom?
No, sir, we are not giving it.
No, right? So, whatever the energy you are giving, all these atoms are going to receive in the same way. Am I correct?
Yes, sir.
Right? Right? Now, when all these atoms are receiving, obviously, simultaneously, all these processes happening within the same fraction of seconds. Okay? To be more precise for your question, now when atom is excited, let's say, think, generally whatever, in physics in general, you try to understand from one atom, then you apply it to larger atoms. Okay? So when you come to one atom, what happens is this atom receives the energy and goes to higher energy level and releases the photon and comes down. While it is releasing, when photon is released, this photon can go anywhere, right? And there are, many number of atoms are there basically. Now that photon can interact with any atom it can feel like. Any atom which is either at the lower energy level or it can be in the excited state also. Okay?
Yes, sir.
I don't know whether you are getting a clear picture
Sir,
or not.
Sir, but one small doubt I have is the excitation of an atom is depending on the energy absorbed.
Absolutely correct. Yes.
If it has a beside atom, a neighboring atom can affect the excitation of an atom or not?
No, why?
No.
How it will affect?
Sir, then even though we are doing doping, we are just replacing an atom. Then the nature of the first atom will not change.
No. See here, when you are doping, what is happening is the original atom energy level will be different from doped energy level energy state. Okay, imagine because if you imagine that silicon and phosphorus, you take it. Okay, silicon energy level, let's say it is somewhere here. Okay, phosphorus may not be here. It may be here. Let's say if it is acceptor, then it will be here. If it is a donor, it will be here. Correct?
Okay, so it means like you're mixing.
Obviously, right? You have to. Don't look at individually. All these things you should, see, really difficult to visualize. Understand that because, for example, in general, when we are directly there, probably the kind of, signaling or, with the hands, whatever it is, I could show, then you can understand it. Because of the virtuality, we are not able to see that. Okay. But you have to couple these things. Okay. At the same time, your donor energy level may not be there. Exactly, may not match with your original energy level. It may be somewhere else. All right?
Yes, sir. Yes, sir. I got it then.
Yeah. Okay. So shall I move on? Have you understood this concept of pumping, metastable state, population inversion, all this? All right. Should I move on? Yeah. Okay. All right. So once you achieve this metastable state, now it's quite simple now. normal population, let's say in thermal equilibrium, you see that this is what happens basically. Energy level, in the energy level E1, you will have more number of atoms. Energy level E2, you will have less number of atoms, and E3 even more less. When it comes to population inversion, this can be this way also, right? So basically, the second energy level can excite into E3, then E3 and E2 will have population inversion. Likewise, this may not be exactly the same thing every time follow. Like I showed you, like here also it can follow, right? 1, 2, and 3. The population inversion can be achieved between 3 and 1. So, likewise, you will have different probabilities basically. All right. So this is how you will get the population inversion. Now you see here, there is a pumping mechanism. Here, whatever you are getting, these are atoms are coming because of the light irradiation or optical pumping that is happening. And this is the resonator I talked about basically. I'll speak about this little later. Now you see, here is the energy level diagram. Basically, at the E1, you will have more number of atoms. This is E2. I just changed the energy level diagrams, that is E1, E2, E3 representation. Don't confuse with that. Now E3 is here. Now at one point of time, you see there is a population inversion here. You see up to certain time, here it is, look at E2 and E1, there is a population inversion achieved sometime. When I start initially, you can see that one. I'll go back and come. When I click that one, you can see for 1 or 2 seconds. See here, sometimes it is coming like your E2 and E1 having population inversion sometimes. Look at, isn't it right? The dynamics is very changing. Look at here, see, have you observed it?
Yes, sir.
Yeah? To understand E2 is greater than E1.
Absolutely. E2 sometimes it is getting greater than E1. So that's what it happens. And that time itself is enough for us. And it all happens in the micro scale. Please remember, it all happens in the micro scale, and it all happens in the very, very small amount of time. That means basically fraction of seconds. Within that, you will get it all this. Okay, this is what is called as population inversion. Now, again, as I told you, why a two-level laser is not possible. This is one of the important questions people ask you in general. For laser action, population inversion is required. A population inversion cannot be achieved with the just two levels, because the probability for absorption and spontaneous emission is exactly the same from the Einstein relation as well, right? Also, then the energy being used to pump the particles into the upper laser state has an equal probability of stimulating them back down. So practically, the electrons revert back to the ground level almost as fast as we pump them up to the upper level. Thus, it is not possible to get more than half of the particles into the excited state. So no population inversion can be achieved in the two-level lasers. So therefore, the two-level laser system is not possible at all. And remember, the lifetime of a typical excited state is 10 to the power of minus 8 seconds to 10 to the power of minus 9 seconds. I hope you got the two-level lasers, whatever I'm talking about. So this is basically two-level lasers. The energy level diagram, at no point of time this E2 can never be higher than the E1. At most you can only do 50%. That's all. All right. Now having the three levels. Now what is three level? Look at, there is level E1 and level E2, level E3. Now this level E3 is called as metastable state. So to achieve lasing, energy must be pumped into the system to create population inversion. So the more atoms will be in the energy level E2 than the E1. Okay. So now atoms are pumped from the ground state E1 to energy level E3 here. Okay. And decay to the metastable state, that is E2. This E2 is a metastable state. Now, relatively, this metastable state lifetime will be higher compared to the E3, right? So if the pumping is strong enough, then after pumping, more than 50% of the atoms will be in the higher energy level, E2, a population inversion will be achieved between E2 and E1. So that is what is 3-level laser here. Okay, look at here. So this is what I'm talking about basically. You have a ground state, excited state, and you have a metastable state. From excited state to metastable state, obviously you'll have a spontaneous emission only. So once all these atoms reaches to metastable state, it stays for longer time. Then you can actually create the spontaneous stimulated emission, so that you get the more number of photons will be released. So and that will trigger the laser action. Okay. So now another, it's not about only 3-level. You can have 4 levels also. Now, what is the advantage of having 4-level lasers? Now, look at here. Low population. Now, remember, why do you need 4-level laser exactly? Now, low population of the lower laser energy level. Now, remember, what is happening is to create the population inversion. There is no need to pump more than 50% of the atom to the upper laser level. The first requirement is this. For example, the advantage with 4-level laser is initially when we had 3-level laser. When you had 3-level laser, so we said that at least minimum 50% should go to the higher energy level. Then from there it comes down to second energy level, correct? So that means basically to create this 50% population inversion or to create the population inversion, you need to have optical pumping or pumping mechanism. That means external radiation, whatever you are giving, it has to be continuously given. So that means, remember, this laser is an expensive deal. And particularly when you use, this optical pumping, all of the money or whatever, expense is basically continuously you have to supply it. It's really difficult thing. Okay. So therefore, continuous pumping is something really, really difficult thing to make it. And giving it continuously is also one of the challenging things. So therefore, in the 3-level laser, you need a continuous pumping. Okay, but when it comes to 4-level laser, you don't really actually require, 50% of the atom to go to higher energy level. Even a small fraction is also enough for you to, get the population inversion. How? See here, the population of the lower laser level is N2T here, decaying rapidly to the ground state. So practically it is empty. Okay, so now this N2 is practically empty. Thus, a continuous operation of 4-level laser is possible. Even 99% of the remaining remaining in the ground state also. Even 1% if you send it, okay, even if you 1% of the atoms from the ground state, if you send it, then it goes to higher energy level, and it comes down to level 3. Level 3, it stays for longer time. And there is another metastable state is there, but before it comes down to E2, it's relatively staying, atoms are staying here, right? So therefore, there is a population inversion achieved between E3 and E2 very easily. Even a small amount of atoms also enough for you to create population inversion between E3 and E2. Are you getting why it is 4-level laser is advantage? Are you getting?
Sir, can you repeat, sir, once?
Yes, I will repeat it. Yeah, sure. I will repeat it again. See, in the 3-level laser, as I said, at least 50% of the atom should be, send it to the higher energy level. Okay, that you agree with me, right? To achieve the population inversion. Now imagine, let's say all the atoms are in the ground state. Imagine only 1% of the atoms are there in the higher energy level. Lower 1% of the atoms you are pumping it. For rough estimation, I'm just giving you, let's say total 1,000 atoms are there. Total 1,000 atoms are there. Imagine 1% only you are seeing. Out of 1,000, what is 1% meaning? 10 atoms. Isn't it right? 10 atoms. 10 atoms you are sending it to the higher energy level, that is in the 4th. Okay. Now 4th energy level is the excitation state, right? So therefore, the type time will 10 to the power of -8 seconds only. So within no time, all these 10 atoms will come down here. Let's say if not 10, let's say 8 or 9 will come down to immediately to level 3. Right? After that, it has to come to level 2. But level 3 is called as metastable state. The lifetime is 10 to the power of -3 seconds. So therefore, it will stay longer enough time at the level 3 before it reaches to level 2. So practically in level 2, at that moment it is 0, isn't it, right?
Yes, sir.
So that means level 3 and level 2 achieved population inversion. Am I correct?
Yes, sir. Comparatively.
Comparatively nothing. It's absolutely. It's not comparatively.
Because
level
level 2 is nothing now, sir.
Level 2 is nothing. There is nothing. There is no atoms are there at this moment. All the atoms are still. Absolutely, right? And not only that, the pumping energy also less compared to 3-level laser. The 3-level laser, you need to give the pumping. Pumping is nothing but, as I said, external energy you need to give it to send the lower energy atoms to higher energy level. Okay, so this pumping is an expensive process basically. Okay, in the 3-level laser, it is always supposed to be done, and it has to, you have to give continuously and more energies to be given. But whereas in the 4-level laser, only 10% of the atom is also enough for you. Sorry, 1% is also enough for you. Okay, so less energy, not even continuous. So still you can easily get the population inversion here. Have you understood this concept? All right. Okay, right. So this operation is something called as, 4-level laser is basically, you can actually give continuous pumping, or even, in a pulse wise also you can give. That is one advantage. And second advantage, less energy you can actually. Third is basically, you easily get the population inversion between level 3 and level 2. So that's the advantage you have. Okay, so that is the reason why 4-level laser system is advantageous over 3-level laser system. Okay, now this is very important concept here. Again, basic components of the laser light. In order to get the laser light, there are few things to be taken care. There's something called active medium. Okay, what is active medium? So now imagine whatever atom you are talking about, that is made of some material. Okay, and that material is something what is called as medium in a way. So it is a material which achieves the condition of population inversion. So something you take, let's say, lasers are happening in the carbon dioxide material, right? Carbon dioxide is the one of the carbon and oxygen atoms. So this carbon dioxide is something called as material now. Okay, now in the carbon dioxide you achieve the population inversion. Okay, through stimulated emission process, lasers. So the active medium may be solid, liquid, or gas. Anything it can be. Carbon dioxide is basically gas, right? Similarly, you can also have, solid materials also. That you will see it. The first laser we talk about is ruby laser. That is a solid material. Okay. The liquids also you have it. Helium neon is a liquid basically. Helium is a liquid in a way. Okay. So helium is also a kind of liquid state one. So the active material is basically one thing where you get the population inversion, where you create the population inversion, and that active material can be solid, liquid, or gaseous state, anything you can. Okay. Now the active medium determines the possible wavelengths that can be emitted from the laser. Okay, because very simple, the reason is active medium itself is nothing but a material where you will have a, energy levels are defined. Now energy levels, when it is defined, whatever the population inversion is achieved between two laser lights, let's say in this case, there is a population inversion is achieved between these two. The difference between these two energy levels is nothing but hc by lambda, and that gives you the wavelength of the laser light. Whatever the light is emitted from here, these two, because of the population inversion, stimulated emission process triggers, and then you get the photons out here, and these photons, with the multiplication process, you get the laser light. Now wavelength of this depends on the difference between the energy levels of E3 and E2, right? So this is determined by the active medium. Okay, so active medium is the one first basic component you have to remember. The second is pumping source. Okay, now pumping source, as I told, what is pumping? Pumping is nothing but giving the energy to the lower energy level, right? So it is the energy source which is used to raise the system to an excited state to achieve the population inversion in active medium. The pump is an external source. Please remember, external energy you are giving. Okay, there are several pumping methods for achieving the population inversion. I'll talk about this pumping mechanism or pumping sources in the next slide. Okay, so first one is active medium, second one is pumping source. These are the two, and there is something called third one is optical resonator cavity. Okay, this is what is another important component. What is optical resonator cavity? Now, like I have shown you in the video, right? Once you get the active medium and pumping source, then atoms will give, or population inversion is achieved. Then you get the stimulated emission process. After that, you get the photons are emitted, right? Once the photons are emitted, it will, all the photons will travel in the same directions, right? Now, these photons should not actually, leave just like that. So what you try to do is you create a mirror, right? Partially, one of the two mirrors you take it. One mirror is completely polished and the other one is partially coated one. Now, remember, just, visualize the video, whatever I have shown you, that two photons will go and hit the one side of the mirror and it gets reflected, and again it undergoes between the two, between the two walls there are many atoms are there, and these photons again go and interact with the few more atoms, then again it creates more number of photons, all these photons again, with the multiplication factor it comes out, again it undergoes multiple reflections between these two resonators or mirrors, then you get the geometrical progressive photons will be generated. So to create amplification process, this optical resonator cavity is something very important. Okay, so this optical resonator cavity is for use to amplify or multiply the photons. So for the multiplication purpose, you use this optical resonator cavity. So now basic components of the laser consist of active medium, pumping source, and optical resonator cavity. These are the three important components you have it. Is this clear now? Yeah. So this is how it looks like basically. Okay. So now see here, these are the two mirrors you have it. This is highly reflective mirror. This is partially reflected mirror. And you have a pumping source here, and this is the laser active medium in which you take it. You put it in some media basically. Okay, put it in glass or whatever it is. Okay, then that one you put it like ends will be attached to the two mirrors, and below that you use the pump source. Let's say xenon lamp or something. You use it to give the pumping source. So, once the photons are achieved here, it will undergo the multiple reflections here and here, here and here. Then once it achieves the, required intensity, and it will no longer stay here, it comes out through the partially reflected mirror. So that's how you will have the, laser pictorial one. Now, pump source. A pump source is a basic energy source for a laser. It gives energy to various atoms of laser medium and excites them, so that population inversion can take place. It is maintained with time. The excitation of atom occurs directly through atom or atom collision. Okay, so I'll just look at here. What is that it is giving? When this what is happening? This is called as optical pumping. You are actually switching on the some pumping switch. Then it's giving you a flash of light. Through that, photons are actually released, and these photons go and interact with the lower energy level atoms, and that receives the energy and it goes to the higher energy level. So that's what here it is. Okay. I'll talk about this, the gain medium and all that little later. And optical resonator, which means I spoke about two mirrors I talked about. This also will come to you later. Okay. Now see here, what is happening is, imagine that there are two photons are there. Okay, there are two photons initially, and it goes to the two mirrors and it gets reflected and it creates four. Likewise, it achieves multiplication factor. Once it achieves the maximum energy or maximum number of photons, then the intensity will be getting double, and it can actually come out through the optical resonator. So it needs to have little bit of energy. So till you get the equilibrium state, all this multiplication factor goes on. That's what is called as optical resonator. Now, again, I'm just trying to give you the how stimulated emission process. One photon creates two, then four, then 8, then like 16. Likewise, you get the gain basically. Now, methods to achieve the population inversion. This is what is pumping mechanism. There are various pumping mechanisms are there. As I told you, optical pumping means, in this case, optical pumping, external energy source like xenon flash lamp, some light is used. Okay, if you use light source, any light source, then that is called as a optical pumping. So when you use light source, that energy will be given directly to the atoms and lower energy atoms, and by receiving that energy, lower energy atoms will move to the higher energy level. This is what is called as optical pumping. There is another, method of pumping is called direct electron excitation, which means, in the, remember in the, you remember the tube lights, okay? Electric discharge will take place, isn't it, right? You apply the voltage, you will have cathode and anode, you will have cathode and anode, right? In the tube light, what happens basically, you have a cathode and anode, yeah, and when you apply the switch, what happens is you are applying the large amount of DC voltage between cathode and anode. And the idea here it's tube, in between cathode to anode, there is a complete vacuum. Okay, but in vacuum there are few stray electrons will be there. Okay, so when you have free stray electrons are there in nature everywhere. For example, when we are speaking, wherever we are in the room, there are stray electrons everywhere. Basically, that is the assumption you have it. Okay, now because you apply large amount of electron, there is a breakdown will happen. Please remember that is called as a dielectric breakdown. Okay, so the dielectric breakdown happens. Then once the dielectric breakdown happens between cathode and anode, large number of electrons will be dissipated basically. So that energy, that electrons, whatever the energy it is coming, that energy is used for the pumping process. So lower energy levels can be, excited to the higher energy level. So this process of pumping is called direct electron excitation. Okay. So the example for this kind of dielectric excitation, electron excitation, is called argon lasers. And for optical pumping, people use ruby laser. Ruby laser is example for this. Okay. And by the way, ruby laser is the first laser. It was invented in the process of laser. Basically, ruby is the first one initially. Okay. Then you have inelastic atom to atom collision, right? Inelastic atom to atom collision. Probably this word is, you must be very very familiar in the intermediate, right? So basically, what happens is, in the inelastic atom to atom collision, in this method, a combination of two types of gases will be used. First, a type of electron or atom will be collide with the one atom. First, electron will collide with the A atom. Then the atom will be excited to the excited level, or metastable state, in other words. Now, while it comes back, once the A excited to the one energy level, then while it is coming back, it releases its energy, right? That energy will be given to some other atom, that is B. Some other atom, that is B. Now again, B will excite, and that B again goes to the higher energy level. I repeat once again. Imagine if you have two atoms are there. Let's say A here. Now what you try to do is, you excite the A to A star. Now when it comes, right? Now when energy of this, when this A star is in the higher energy level, it's supposed to come back. When it comes down, then it releases energy. Now this energy will be given to the second atom, which is in the ground state, that is B. Now by receiving this energy, the B will move to B star. And this process is called inelastic atom to atom collision. The example for that laser is helium neon laser. I'll explain you what is this helium neon laser, how this inelastic atom to atom collision will take place in that. Is this clear? Inelastic atom to atom collision and direct electron excitation. Okay. And then chemical reactions. You can also use chemical reactions. Now you remember that there is something called in the chemical reaction, endothermic and exothermic reactions. Have you remembered this?
Yes.
Right? Endothermic means what? Can anybody please tell me?
Sir, energy absorbed.
So that means basically you need to give energy to take place that reaction. Correct?
Yes, sir. Energy
to take place reaction, you need to give some energy. Now there are other reactions where the moment you mix it, then what happens? Obviously, energy will, when you mix two chemicals, the energy will be released. That is called exothermic reaction. Okay? So endothermic and exothermic, remember that. So energy is supplied by the chemical reaction between two or more atoms. Okay, so that is what is. So basically here, in general, exothermic reactions are used. You use two chemicals, and when you mix these two chemicals, exothermic reaction will take place, therefore energy will be released. That energy will be used in the pumping process. That's how you use this chemical reaction. So these are the four different methods people use it. Is this clear? Methods of achieving population inversion or pumping process. Pumping methods, these are called pumping methods. Is this clear? Yeah, okay. Now, laser action. How laser action takes place? Remember, the first process in that laser action is pumping process. Initially, the atoms in the ground state, and it are, the moment when you do the pumping, all these ground state atoms will go to the, or some of the atoms will be go to the higher energy level. The second process in that is population inversion. Once it goes through that, you have a metastable state, then you get the population inversion between two energy levels. Okay, that is the second, process in that. Now, third, once you achieve the population inversion, you need to get the stimulated emission process. Okay, well, how do you get the stimulated emission process? Once you achieve the population inversion, that means more number of atoms are there in the higher energy level compared to lower. So at that process, at that time, you instant the photon at the higher energy level or excited atom, then that triggers the stimulated emission process. Okay, so once you get the stimulated emission process, what is the next one? That is the amplification one, right? So this amplification, I explained you, 2 will create you 4 photons and 4 will give you 8, and the 8 will give you 16. That's kind of, geometrical progression will take place. Remember, this progression will take place, a geometric progression or amplification will happen because of the resonator. Please remember. So you have a 2 optically, polished mirrors. So that mirrors will be acting like a optical cavity, resonator cavity. Because of that, the multiple reflections between these two mirrors, then you get again and again the same photon will go and interact with different atoms. So therefore, you get the more number of photons will be released. So that's how you get the amplification process. Finally, laser. Once you achieve the amplification, then you get the laser light. So you can see now, light amplification by stimulated process. That is what is laser light. So there are 5 steps out there. Pumping first, next population inversion, third stimulated emission process, fourth amplification, then you get the finally laser light. Is this clear how you get the laser action? Is that clear? Yeah, okay. So this is the black diagram in a way. Okay, so in general, this is the active medium in which you take it. These two are optical resonators, mirrors. Then you give the source of energy, that is the pumping, to this active medium. Then you get the population inversion here. Once you achieve the population inversion, then you actually give the again external light. Then you get the stimulation emission process into the place. Then after that you get the amplification process between the optical resonator. After that you get the laser beam of light will come into the picture. Okay, this is a black diagram. Again, this is a working principle here. So again, the same thing basically, active medium, totally reflected mirror, partially reflected mirror. There is amplification between these two will happen. Once you get the better, high intensity or sufficient number of photons, you get it, then it comes out through the partially reflected mirror as a laser beam. So up to this, is there any doubt you have it? The person who is recording, you can stop it actually. I'll stop here, class. Yeah. Yeah. Any doubt?